Good morning. I am Ganesan Ramanathan. I will be talking to you about radiation applications in India. The outline of my talk will be, first I will talk about nuclear reactors for electricity generation. Second, we will look into medical applications. Third, industrial applications, and some applications in agriculture and research. The picture shows the Bhabha Atomic Research Center, which is the birthplace of nuclear technology in India. I had worked there for over 30 years, and the bottom figure shows the modular laboratories, which is the longest building in India, which comprises of 300 rooms in 3 floors. This picture shows the Atomic Energy Regulatory Board. The Atomic Energy Regulatory Board was constituted in mid-80s by Government of India based on the Atomic Energy Act, which was promulgated in the year 1962. This Atomic Energy Regulatory Board is an independent body with the board of directors from various universities and other organizations, and the board ensures the safe use of radiation in nuclear as well as medical and industrial applications. The picture shows the 3-stage Indian nuclear power program envisaged by Dr. Homi Bhabha, and then subsequently it was followed by the other great scientists. The first stage consists of the pressurized heavy water reactor, which is also called the CANDU reactor. With the help of Canada, this reactor was developed, and these reactors make use of the natural uranium as the fuel, which is considered as the most safe type of reactor. And these reactors, they produce about 220 megawatt electricity, and they require heavy water for their operation. So a number of heavy water plants also has been established by the Department of Atomic Energy. These products of these reactors, there is a depleted uranium and thorium and plutonium, they are fed into fast breeder reactor, which is located in Kalpakkam, Chennai. And this fast breeder reactor, it converts thorium into uranium-233, and it also produces electricity, so of about 500 megawatts hour. This uranium-233 is used in the third stage of reactors, mainly using uranium-233, and this uranium-233 is obtained from thorium, which is available in abundance in the Kerala beach sand. So once we achieve this third stage, then there will be no shortage of supply of nuclear fuel in the country. This map shows the location of various nuclear reactors in the country. The first nuclear reactor to be for electricity generation was installed at a place called Tarapur, which is closer to Mumbai, and this reactor was obtained from General Electric Company in USA. And in 1973, when the Pokhran explosion occurred, the fuel supply to these reactors were stopped, and the BARC scientists, they developed a mixed oxide fuel to replace the fuel from the General Electric Company. And then they successfully ran this reactor, and this now supplying electricity to the Maharashtra grid. Then we had the reactors installed at the Chitradurg in Rajasthan, and then Narora in UP, Kaiga in Karnataka, and Kakrapar near Surat, and then of course Chennai, Kalpakkam, and lastly we had 2 big reactors installed at Kudamkulam with Russian collaboration. And this Kudamkulam is located closer to Tirunelveli, and they produce electricity and supply to the Tamil Nadu electricity grid. Then moving to the medical applications, we had 2 big applications. One is called the teletherapy, and in teletherapy the radiation source is kept at a distance from the patient, and the radiation from the source it kills the tumor in the body of the patient. And these machines, they are available of two types. One is using the radioisotope called the cobalt-60. So we have cobalt-60 machines, and then we have electrical machines called linear accelerators. And these linear accelerators are different than cobalt-60 because cobalt-60 produces only photons of average energy 1.25 MeV, whereas the linear accelerator produces photons of much higher energy. And in the evolution of teletherapy, the cobalt-60 could be used to treat only up to a depth of 5 centimeters inside the body, whereas the deep-lying tumors required higher energy radiation. That's what prompted the development of medical linear accelerators. These accelerators, they provide photons varying energy from 4 MeV to about 20 MeV, and they also produce electrons. So we can use both photons as well as electrons for the treatment. That is the advantage of linear accelerator. And the cobalt-60 has got a half-life of about 5.2 years. Therefore, every 10 years, almost after 2 half-lives, one may have to replace the source, and that has become quite a tedious procedure. Whereas the linear accelerator requires maintenance, and it also has got a life of about 10 to 15 years, but it doesn't require any source replacement, and that is the advantage. So we have over 250 cobalt machines in the country and about more than 400 linear accelerators. Now the next big mode of treatment is called the brachytherapy. In brachytherapy, the source is brought close to the position of the tumor, and the radiation is delivered to kill the tumor. Mostly the isotopes called iridium-192, cesium-137, strontium-90, and iodine-125, and cobalt-60 as well. They are used for this type of treatment. And the machines used for this treatment, they are called the afterloading machines. The afterloading machines, the sources will be kept in the safe place inside the machine, and when the treatment is required, the sources will be brought and inserted into the body of the patient through a catheter. So this treatment is becoming more popular for the treatment of prostate and breast cancers. There are about 300 the remote afterloading machines and about 50 manual afterloading machines in the country. Then next we see a list of radiotherapy facilities in Tamil Nadu. There are over 50 facilities in the state, and starting with Amblikai, Christian Cancer Center in Amblikai, we see a large number of hospitals in Chennai, and then Coimbatore, and then Erode, Kanjipuram, Thanjavur, Madurai, Salem, Tirunelveli, Tiruvarur, and Tiruchirappalli, and Kanyakumari, etc. All these places, the machines are there, teletherapy facilities are there. Then this picture shows the advanced teletherapy machines. The left extreme machine is called the Gamma Knife. Gamma Knife has a source of more than 200 cobalt-60 sources arranged in a spherical helmet, and the radiation is brought through a fine collimator, and this is used to treat the brain tumor, because the tumor in the brain has to be very precisely treated, because brain has got very sensible organs and sensitive tissues, so they have to be spared. So for that reason, this very fine pencil of beam is used. And the bottom figure shows a cobalt-60 teletherapy machine, which is called the Babatron, developed by BARC. This Babatron has got some special features, and I can proudly say that I was associated in the development of this Babatron. Then we have the brachytherapy equipment shown in the middle. This is afterloading machine. And then we have the conventional radiotherapy medical linear accelerator. These accelerators, they now come with flattening filter-free beams, or the true beams, as against the conventional filtered beams. And then they are also provided with what is called the cone beam CT for imaging the patients. This picture shows the left extreme picture shows the proton facility which has been established at Apollo hospitals in Chennai. This proton therapy is becoming popular because it has the unique advantage that the protons can directly reach the tumor, avoiding the surrounding healthy tissues. So this provides an advantage in time, because the conventional treatment using the other linear accelerators, the beam is a broad beam, where although it is shaped by several methods, but still the apart from the tumor, the surrounding healthy tissues also may be exposed. So to overcome this bad effect of the radiation caused in the healthy tissues, a fractionation method is used. In the fractionating method, a total dose of say 60 gray is divided into 2 gray each, or 30 fractions. So the patient will have to come to the hospital for 30 days, and each fraction will be delivered. So whereas in the case of protons, since the surrounding healthy tissues are spared, the entire 60 gray can be given in a single shot. So that is a big advantage. Then we have the other two machines. The one machine on the left is called the CyberKnife, which is equivalent of the Gamma knife, but making use of the linear accelerator. And the other machine is called the tomotherapy machine. Tomotherapy makes use of the circular arc treatment and imaging combined, and this machine also is a special machine. Then we move to the diagnostic applications of radiation. There are two modes, two machines mainly used. One is called the cath lab, or the cath lab is used for interventional radiology. It is used during the interventional procedures, and there are about 1,800 machines in the country. And then we have the other machine called the computed tomography, or called the CT. CT provides a three-dimensional image of the parts of the body, like the brain and other parts. Where it makes use of the X-rays, which are sent through the various slices of the body, and then the intensity of X-rays, transmitted intensity, is used to construct the three-dimensional image, as against the conventional X-rays where they produce only a two-dimensional image. There are over 4,000 CT. Next, we will see the application of X-rays for diagnostic purposes. The earlier methods, they are called radiography and fluoroscopy. And here in radiography, a fraction of a second exposure is given, just like in a photograph. And then the image is recorded on a photographic plate. The normally this is done for chest and other abdomen and other places. For chest, there will be a separate chest X-ray stand, where the patient will be asked to stand, and then the beam will be directed onto his chest, and a photographic plate will be kept at the back, and the image will be recorded. And this is a very popular method And then these machines also have another type of mode of treatment. This is called fluoroscopy, and this mode of diagnosis, rather, this fluoroscopy is one in which the tube is operated at lesser current for a longer time, and the beam, X-ray beam, uh, passing through the patient will fall on a fluorescent screen, and the doctor will be able to observe the image on the other side of the screen, and the patient will be normally injected with radiopharmaceutical, and the flow of this radiopharmaceutical through the intestines or abdomen can be visibly seen on the fluorescent screen by the doctor, and he can locate the block or the tumor, and then he can proceed with the treatment. And there are about 55,000 such machines in the country, and earlier part of my BARC work, we used to go for radiological protection surveys of these X-ray machines. I have visited a number of hospitals in Tamil Nadu, both government as well as private hospitals. Our job was to check for the radiation safety, and we used to give them advice on how to improve the safety. We used to measure the radiation levels, and then go through all the practices so that we can recommend a better practice to reduce the dose. Now that has been transferred to the CSIR scientists, they go to the hospitals and they have a questionnaire, and then they ask the people various questions connected with this radiography and fluoroscopy, and then they send it to the AERB. Now the next method is the nuclear medicine. Nuclear medicine is used for both diagnosis as well as for treatment. It makes use of open isotopes like thallium 208 and technetium 99M, iodine 131, and fluorine 18. And these radiopharmaceuticals, they are all short-lived isotopes, but they provide better imaging qualities. The F18 is used in PET-CT scanners, and iodine 131 is mostly used in the treatment of thyroid cancers. There are about 310 facilities of PET-CT, gamma cameras, and radionuclide therapy facilities in the country. Then we have the medical cyclotron. The medical cyclotron is a machine which produces these short-lived isotopes for nuclear medicine, and the F-18, for instance. And these cyclotrons are very, very useful because the isotopes are short-lived, so they have to be immediately retrieved and then used. So these cyclotrons are there about 18 facilities in the country. Then we have the industrial applications of radiation sources. The industrial application, the major application will be what is called the radiation processing facilities. The radiation processing facilities, they make use of an intense radiation source, and the materials like food, vegetables and fruits, and these other spices, etc. They are all irradiated with the radiation from these sources, and their life is extended. So these facilities, they are very, very useful in preserving the vegetable. For instance, the onion and potatoes, they get easily spoiled by sprouting. So these onions and potatoes, when they are exposed to this intense radiation, then the sprouting is removed and they can be preserved for a longer time. Same with the case of fruits. And here I would like to narrate an anecdote where in 2006, President Bush visited India, and he liked the Alfonso mangoes, and he asked them to be exported to the White House. But in America, there is a Food and Drug Administration, FDA. They refused to import these mangoes because they suspected that mangoes may have fruit flies and it may damage the American agriculture. So then finally a decision was taken to flow flew American scientist, and this American scientist, he came to Nashik, where this radiation processing facility is there, and he irradiated the mangoes, examined them after radiation, and then certified them that these mangoes don't have fruit flies. Then mangoes were exported to Washington. Now these sources used mostly are cobalt 60, and they are kept in a pool of water because the intense source emits a lot of heat. And then we have a facility called Isomed in BARC. This similar facility with a large radiation source. This is mainly used for sterilizing the medical products. The medical products like needles, syringes, etc., they are brought in cartons and they are taken around by conveyor belt, and when they are brought in front of the source, they get sterilized without opening the carton. So there is a big advantage, and it can be straight away used, saving a lot of time in the conventional method of the making them sterile. So this is a big facility. And then there are linear accelerators, mostly electron accelerators, which are used for irradiating the spices like cashew nuts, pepper, cardamom, etc. Mostly they are available in Kerala, and so the linear accelerator, which is a spice irradiator, is called. It is located in Kerala, so that all the spices will be irradiated and their life extended, and so that they can be exported. There are about 21 gamma irradiators, and there are about 11 accelerator facilities. Then we have the industrial radiography, which is also known as the NDT, or non-destructive testing. So in the industrial radiography, radiation source is used to cast an image of bulk materials, which are say boiler vessels, and these materials, after they are produced after by welding or casting, then if there is any defect in the weld or cast, that can be found out by the non-destructive method using the radiation source. The most widely used source is iridium-192, and the this technique is sometimes used in what is called the open field radiography, where the source is kept in the middle and all the samples are arranged in a circular ring form, and then the photographic plates are kept on the back side of these samples on the big vessels. And then after irradiation, the morning these photographic plates are analyzed to find any defects in the wells or castings. And then there are also some X-ray machines which are used for this type of purposes, and there are about 560 facilities with 2,772 equipments in the country. Then we have the gamma irradiation chamber, which is nothing but a huge source, again, which is located inside a shielded container that is shielded mainly of lead, and this source will have an opening at the center where a tubular column will be inserted, and the column at the bottom of the column there will be a place for placing the specimens like biological samples or other samples which have to be irradiated with a very high dose of the order of megarad dose levels. So these circular rod column that can be moved by a motorized movement. So after placing the samples, the column will be lowered, and then the samples will be brought at the place where the source is there, and they will be exposed, and then they will be retrieved later. There are 114 facilities with 120 devices in the country. Then we have the nucleonic gauges. This is most widely used industrial use. These nucleonic gauges, most of them they come often as part of the turnkey projects when big industries are erected with American or European collaboration. And these gauges are used for finding level, density, and composition of the processing materials online without non-invasive method. So this gauges, they are widely used in big steel mills like Bokaro or Rourkela steel mills, and they are also used in thermal power stations. And I would like to quote an example of such an use in the Ennur thermal power station, which is close to Chennai. I happened to visit there for a radiological protection survey. These thermal power stations, they have huge containers called the hoppers, where the coal which are brought by goods trains, they are dumped into the hoppers, and then they are emptied into the furnace gradually, and then it is burnt, and then electricity is produced. So the control of these levels in the hoppers is a very important thing. So that is achieved by using the level gauge to find out whether the hopper is empty or is half full or is completely filled. So the we have three gauges normally. One side the source is kept, on the other side the detector is kept, and if it is empty, then the full radiation will reach the detector, and the signal will show that it is empty. And when it is full, the coal will be absorbing the radiation, and the signal will be brought down, so that will show the coal is full. So in such a way, this control of the coal supply into the furnace is regulated. And there is another example is I would like to quote is where in a place called Kudremukh near Mangalore, where iron ore is dug up. The Kudremukh is at a height of 60 kilometers above the sea level at the Mangalore port, and the dug out iron ore is to be sent to the Mangalore port by making it a slurry and then sending by pipelines. When they reach the port, the water has to be segregated, and the ore alone is exported by shipping to countries, mostly to Japan. So this moisture in the ore after the water is removed has to be found out. So there is an online moisture gauge that is fitted with a neutron source and a detector. A fast neutron, when it interacts with the moisture, it gets converted into the thermal neutrons. So the detector kept on the other side, which is predominantly a thermal neutron detector, the increase in the signal will show the amount of moisture, and that is used to control the the moisture in the slurry, and this is a very useful thing which helps the uh, iron ore company to save fines being imposed on them by the shipping companies. And we have the other sources like Californium 252, Americium beryllium. There are the neutron sources which are normally used in these type of gauges, and there are about 1920 facilities in the country, that is including all the nucleonic gauges and the moisture gauges. So these gauges are extremely useful, and they have a very small source, and so the protection is not very much needed. Next, we have the well logging applications, where radioactive sources are used for well logging application for exploration of oil, coal, geophysical logging, etc. The sources used mostly are neutron sources, the americium beryllium, radium beryllium, etc. And these sources, they emit the fast neutrons, and oil being a hydrocarbon, the hydrogen in the oil and the neutrons, they interact and convert these fast neutrons into thermal neutrons or low energy neutrons, and the gauges are fitted with a thermal neutron detector, that is boron trifluoride counter, and the amount of thermal neutrons recorded, that will tell the extent of the oil percent or coal percent. In addition, we can also get the density information, where the same logging device will have gamma source like cesium 137, and the scattered radiation from this gamma device will be recorded in ionization chamber, and the signal from the ionization chamber will be giving the information about the density of the soil. So the moisture and density both are very useful in laying foundations for big multi-storied buildings, and it's also used in scientific farming, where the extent of the water flow in the soil is found out using these gauges, and then they are used to decide the water scheduling. So this they normally use sources of the tens of kilobecquerels to gigabecquerels, and there are about 51 facilities in the country. Then we have the radiation sources which are used in research applications and consumer products. The consumer products such as the smoke detectors, the thorium gas mantles and starters, and various tritium luminescent devices. They are very much used, and the smoke detectors, for example, it makes use of a small americium 241 source, and the radiation, which is both alpha and gamma radiation, will flow through an ionization chamber, and when there is normal air, there will be a signal which will be recorded. But when the smoke is present, it will also flow through the chamber, and smoke having a lot of carbon, it will absorb this radiation, and the signal will be brought down, and that will trigger an alarm. So these smoke detectors are very commonly used in many Western countries to find out about to prevent the fire accidents. And there are the luminescent devices which are used in watches to find out the time during the night time, and also there is luminescent paints are applied on the roads to for the vehicles to find out about the various bends or curves in the road. So these are very useful applications, and there are about 16 facilities in the country. Then we have consumer scanner facility, the container scanner facility. This container scanner is a kind of port through which the containers carrying materials they will pass through. If they have radiation content in the materials, then this facility will be used to find out. For example, after the Fukushima accident in Japan, the Japanese cars which are exported to many countries, especially say Australia, where I was working at that time. The cars will be taken through these ports to find out if any residual radiation is present in the car. So that is the exercise which we did. So these facilities, they are very useful, and there are about 15 scanners. They mostly make use of cobalt 60 source and sources as other applications. The source will be kept on one side and the detector on the other side. So there are about 15 scanners and equipment. Then we have facilities using sealed sources. These sealed sources, which are used for medical applications, and the and then for education, research, and calibration purposes, the activity ranges are very, very small, and there are about 166 facilities. And then we have facilities using unsealed sources. Unsealed sources are used in various research and academic institutions such as agriculture, veterinary science, and traces studies, etc. So they are also of very small activity, and they don't pose a big radiation protection problem. So they are about 177 facilities in the country. Then when we look at the overall scenario of radiation isotope applications in industry, mainly they are characterized by quick, easy, clean, and cost-saving techniques. Now there are two ways. One is using the sealed sources, and we are seen in radiation processing and in radiographic testing, that is NDT, and gamma scanning, where the scanning of we are seen in the containers scanning, and then industrial tomography. Tomography is finding the three-dimensional information about the materials, and then nucleonic control system, where we have seen all the nucleonic gauges which are used for level, density, and composition of the materials. And then we have radioactive tracers, which are used for flow rate measurements and inventory control in chemical plants, and leak or blockage detection in pipelines. This is a very important application in the Gulf countries where the oil is taken through long pipes. If there is a corrosion inside the pipe, that may result in the pipe bursting and oil getting lost. So the radiation, radioactive traces will help in locating such a place where the pipe burst has occurred. Otherwise, there will be a radiation gauge which will be taken by jeep and run along the pipeline, where if there is corrosion is there, then the gauge will show, and then the pipe will be the oil flow will be stopped, the pipe will be broken and then repaired, and then the flow will continue. So this is a very popular method in the Gulf countries. And then we have RTD studies in chemical reactors. So radiation tracer devices, and then we have silt movement studies in harbors. This is a very important thing, because the silt movement will decide whether the ships can be safely docked in the harbors. So that is easily studied using the radioactive tracers. Then we have the various applications pictorially shown here. This is film thickness is one application where very thin film, the thickness of the film has to be uniform. That is found out by nucleonic gauge. The one example I can quote is the tire industry, where tire is actually constructed by having a thin film over which the latex is coated, and then the various they are all rolled and compacted to get the tire. So in these things, the films have to be films, and the latex coating has to be of uniform thickness, and that can be found out online by the nucleonic gauge. If this is not found, then the tire may have not a regular shape, and it may wobble. So this is a very important thing in the case of production of tires. And then paper thickness. This is again the thickness of the papers will also decide the quality control in industries. So this thickness can be found out by having nucleonic gauge. And there is a beverage level. This is also found out using the nucleonic gauge. And similarly, oil levels, they are also found. I would like to quote only one more this thing, because the density of tobacco packed in cigarettes, where I visited an Imperial Tobacco Company near Bangalore, where there is the cigarette paper rolls, they come, and then in which the tobacco is packed, and the density of packing has to be uniform, otherwise the manager was telling the consumers will find out that, and they will reject the cigarettes. Therefore, the online density gauge is there, which will record the density, and if there is any variation, then that paper roll will be removed from the conveyor belt, and then the other process will continue. So these are some of the interesting industrial applications